Good afternoon, everyone. All bit of lovely people that we have from SSPC, from UL and beyond. So many faces that I know, but seeing you in person. Right, so without further ado, let's see what are we doing with the MOFs and PFAS. What are PFAS? They are what represent forever chemicals. So that's a proverb for why they're forever, because they never leave our body. They check in, but they never check out. So that means when they get into our body, they get bioaccumulated for a prolonged period. And because they are special chemical that I'm going to show you in a couple of minutes, they don't check out. That's a pretty sad story in a way. But before that, let's see the happy bit. This is what caused me to move back to Limerick. And before you ask me the question, why did you come back again to this rainy town? Because I think I really love this place and enough kind of incentive to come back and explore my own teeny tiny research group, which has 2 members right now in this room, Asif and Bhavna, 2 PhD students, and there are a couple of interns that have worked with me over the past year. It so happens that I've just clocked a year as I speak and just moved into my second. So over the years, by the way, before I move into the research bit, I think I have to thank all these funding agencies. Mike already said about the Humboldt Foundation, the Marie Curie grant that came along as well, and the SFI grants, the IRC postdoc, everything. So all of them kind of have sustained over the years whatever little journey I have had, all the credit goes to them. Right, so our interest in the group that I call NanoSorb, nanoporous sorbents, standing for the acronym NanoSorb, is in the interface of supramolecular chemistry and material science, more precisely porous materials. So what do? We look at purification of air and purification of water. In this particular slide, I'm just focused upon, and this particular presentation actually, I'm just focused upon purification of water, and that to just drinking water. So the right quarter of my slide has agrochemicals and pesticides and some industrial effluents. And at the bottom row of this part, you have the PFAS, the notorious PFAS, which is a group of chemicals. There are about 9,000 chemicals which fall under the classification, the umbrella of PFAS. So out of them, they are the most notorious ones, which are pretty much prevalent. And right now, as I speak, we have consumed it with just being oblivious about it. So how do we get that? So water scarcity, as Mike already spoke, is one of the big grand global challenges. But to be very honest to you and be explicit about this issue, this is not really a developing nation's problem. And to just look at what the numbers show, because data won't lie, even in 2021 in Dublin, there is 81 pesticides that were detected in the water collected. And the situation is far worse if you look at mainland Europe. So what are I'll try to shift focus on PFAS, because that's the forever chemicals that I'm dealing with this particular project here. The 3 particular notorious ones would be the ones highlighted, PFOA and PFOS, perfluorooctanoic acid, and the perfluorooctane sulfonic acid. These 2 are right now falling under the EU REACH list, which are kind of not really banned substances. However, they are restricted as contaminated. The legislations in the states are actually far higher, and I will come back to that in a moment. But before we get to that, let's see what is the definition of PFAS. As I say, 9,000 of them exist. This actually picked up speed. This only came to the fore in 2011, as early as 2011. This first was reported by DuPont. But then it picked up pace in such a way that right now we sit over a big problem, and these Teflon pans are at the very core of it. So when we fry our omelets, that's where it starts to bioaccumulate. And why? Simple, carbon-fluorine bonds. Because carbon-fluorine bonds are the most well-known strong bonds that lie in organic chemistry. We have studied it, Physical Chemistry 101, 410 kilojoule mole inverse. That's the bond energy for each. And if you have those many of that in each of these, that will lead to spectacular properties in terms of surface energy, that is the minimum surface energy, leading to minimum surface tension, and that would mean high durability. So these are special. They are like the avengers of the chemicals in a way, because they will never degrade, and forget about biodegradation. So that's why they are great to use, because once you make them, they stay as it is. Right, so why it's a problem in the mainland Europe, and particularly in Belgium, Germany, and a couple of other European states, is because these numbers that you see on the placards is the level by which the numbers are skewed at the higher end. So that means just look at this particular number over here. 257,000 microgram per liter of PFOS was recorded at Antwerp, which is the Flemish region of Belgium. On the contrary, Minnesota, which has a legislation in place, has the safety limit of 0.015. How scary is that? So when this number was first looked at, people actually commented, and there are multiple reports in Guardian, in CEN, and so on, that there must be some problems with decimal places. This must be a typo, yeah? But there was a follow-up report which said, nope, this is how it stands. And so we are actually sitting on a pretty massive problem, just nobody wants to talk about it in a way. Right, so how does industry do what needs to be done? That is the decontamination of PFAS from drinking water. The only two methods that can do this job in a way is nanofiltration and reverse osmosis, RO and NF. But to do this, you need to have high capital expenditure or high operational expenses because of the way it works. It needs activated reduction or activated oxidation processes. So to kind of two things. One, high energy footprint, as Mike also mentioned. In a number of purification processes, this is the challenge. So high energy footprint and high cost of doing it makes it cumbersome. So we need to somehow find a sweet spot of how to do things in a better way, because again, we are coming to these distillation towers. Right, so this is our approach, what we have done in this regard. We wanted to see if the high surface area that MOFs kind of stand for and represent in a way, are they really important? Is the pore size really that important, or is the pore functionality, or rather the surface functionalization makes the cut in terms of dealing with this problem? So we chose a very well-known, stable, easily scalable class of MOFs known as UIO. The name stands for University of Oslo. It's a very well-known MOF, perhaps the most well-known, in fact. It's 2008 JAX that started everything. So we synthesized 4 of these, 4 analogs. You can see how they differ from each other. So each of them have the same kind of pore structure, but the functionality changes. So hydrogen, nitro, amino, and tetrafluoro. And we just didn't leave it to the as-synthesized MOFs. We also made the polymer-coated versions of them. By that, I mean the low-cost organic polymer organosilicone that you see here. So we made actually 2 attempts. One is the PDMS, the rather conventional polydimethylsiloxane polymer, which didn't really work out in our favor because the coatings were much thicker, and the hydrophobicity component was addressed. So we ended up publishing this paper last year, but it couldn't do what it was primed to do in terms of PFAS. But the organosilicon part, which is this actually did spectacular in terms of PFAS, which I will come in a moment. Before I get to the PFAS performance, just look at the characterization part of the organosilicon coated ones. And one striking observation in this regard is how the 2 different hydrophobicity signatures differ. This is the pore hydrophobicity. This is the pristine pore. These are the coated ones. These are the water adsorption isotherms, which represent the pore hydrophobicity. This one here is the surface hydrophobic signature, and that means the water contact angles. What this tells you from 0 degrees, so we started from the hydrophilic. All 4 of them were hydrophilic, registering 0 degree of water contact angle. And this one ended up super hydrophobic. So that meant we did only change the surface property, but not anything on the pore hydrophobicity. The morphology was retained, saying the crystallinity and the PXRD, everything was okay. Going forward to, let's look at the batch adsorption performance, and this is what led us to believe that UIO66 and 66F4 are clearly winning over everything else in terms of addressing the performance in as quick as 30 minutes. So the job was done in 30 minutes, whereas GSE, the benchmark right now is granular activated carbon or powder activated carbon. They do it over a course of 24 hours. Instead, this could do it in half an hour to an hour. That's not all. If we look at the detailed kinetic study, that study validated this observation of batch. Moreover, we also looked at trace. So just when I spoke about the previous two performance analysis, look at the contaminant concentration here, because concentration is the king in this regard, because concentration, if you take it to higher concentration, everything will start to perform in a way. But if you really take it to the trace concentration, such as 2 microgram per liter, which is the real relevant concentration in water, that's where it starts to handicap. Most materials will falter. So if we now look at the carboxylic acid-based PFAS, that's how the small ones kind of underperform. The bigger ones outperform in every regard. And there is a clear trend, as you can see. So higher you go, higher is the PFAS size, better is the performance. This is rather counterintuitive, right? Because normally you have a smaller molecule that gets trapped more. Because if porous size was the factor, this would be trapped more. But perhaps if you just bear in mind that this is in water. All these studies were done in water, immersed, and under stirring. So this means hydrodynamic radius is the relevant parameter and not the kinetic diameter of just the free fluid. Yeah? So if you consider hydrodynamic radius of each of these sorbates, that comes out that at this case you see a spike here from this to that. For perfluoropentanoic acid, there is a spike. And that spike is because that's the first molecule where that can enter the pore size of UIO66. But beyond that, it all goes in and comes out because there is no real packing of the sorbate-sorbent. We did a lot of regeneration studies, which led us to again believe that methylone NaCl is the best regeneration solvent among the ones we studied, that is these three at the top. And long story short of the regeneration studies is the GenX couldn't be really done at the highest level that we wanted to, but the PFOA and the PFOS could be regenerated at the level that the next stage of introspection need in this case. Ion spectroscopy led us to the binding sites, and that alluded to this particular pair being the critical one. So the metal, the zirconium metal oxo cluster was supposed to be the binding site to the carboxylic. When we looked at MD simulations, this was opposed by it. Rather, so MD simulations was performed, and what was found is rather the interactions were taking place with the polyfluoroalkyl groups, which is not the case. So this was leading us to a paradox in a way, and that's where me and Jennifer, we worked at SSPC downstairs, literally from my lab, and we found out that high-angle STM, so high-angle annular dark field STEM, that imaging showed us that the percentage of this PFAS molecule just populate at the right places so as to indicate that the zirconium oxo clusters are behind it. So this piece of data was kind of consolidated. The fact that metal oxo clusters, and more you bind the metal oxo clusters on a surface, better adsorbent will it be, and not the porosity. So it really lived up to the surface hypothesis that we had in mind. So just to summarize the key take-home messages, first thing first, trace level, less than 2 microliter PFAS scavenging is reported for the first time. And when I'm saying first time, I'm not trying to really overhype just among MOFs. I'm actually telling it among all materials. So that's something that is across all sorbents. And yes, there are other things that I already touched upon.
Okay, thank you.